Shirley up from Slack. She's going to talk to us about Dune as the next generation solar neutrino experiment.
Thank you. So Dune is a funded experiment under construction right now. At the cost of above $1 billion, that will be the leading experiment in the next generation particle project in the US. So officially, Dune has 3 main science objectives: measuring the CP violation in neutrino sector, observing the next galactic supernova neutrino burst, and then testing proton decays. So in our project, today I'll talk about, we propose that Dune add a 4th science objective, measuring solar neutrinos. And the reason is we believe that the theoretical promise of doing solar neutrinos in Dune is incredibly compelling. And what's more important is that the results that we will present later, we think should be practically experimentally achievable. Hopefully by the end of my talk, you are convinced of these 2 points as well. And let's get started. And please stop me anytime if you have questions. So the whole physics point of the talk can be nicely summarized by this figure. So on the x and y axis, one is angle and one is delta m squared, and with subscript 1 to sector. These are 2 oscillation parameters that governs neutrino oscillation. And the colored contours show 1, 2, 3 sigma measurements from combined solar neutrino measurements we have today. And the black contours show 1, 2, 3 sigma region of the measurement from reactor experiment Canland. And the angle basically agree with each other, but the delta square, there's about 2 sigma discrepancy. So that's the premise of the whole talk. So for my introduction, I'll explain a little bit what these 2 parameters are and how they actually govern solar neutrino oscillation. And then I'll talk about experimentally what are the challenges that we face to resolve this tension. More importantly, why can't we wait for, say, 5 more years and hoping that the solar control will shrink to resolve this tension? And lastly...
So what is the tension? I don't see the tension.
Okay, 2 sigma. And part of that I will talk about...
Why is 2 sigma tension? Happens every day.
Just 1 sigma, right?
So the significance of this change from group to group, but it's about 2 sigma for like joint fit.
Okay.
So I thought the standard word for 2 sigma is a tension, or is a hint, or
my standard word for it is I don't care. But,
okay.
Maybe someone cares. That's okay.
That's fine. Then I can also talk about why we should care about this and why we want to do better measurement of this regardless. And lastly, for our project, I'll show that how Dune can improve this measurement. Okay, so first, just a brief introduction on solar neutrinos. So the sun is powered by nuclear fusion reactions, and the net reaction is proton fused into helium-4. And in reality, this reaction is proceeded through 2 chain reactions. The proton-proton chain, which produce 99% of the energy, and the CNO cycle. So inside these chain reactions, there's individual reactions that actually produce electron neutrinos. And all of the electron neutrinos from each branch are plotted here, and the PP chain reactions are written here. You don't have to look at these reactions. The point is, actually I already explained before the talk, what's the neutrino energy? So roughly speaking, it goes from 0.1 MeV to about 20 MeV. So this is a nuclear physics process. And the y-axis shows the neutrino flux. It's very large. If you haven't heard about this, if you put up your thumb towards the sun, then every second there are about 10 to the 10 solar neutrinos passing through it. So that's just a cute fact. And roughly speaking, I think the physics of solar neutrinos can be nicely divided into lower physics, a lower energy branch, and higher energy branch. And this is something good to keep in mind. So if I do a cut at 2 or 3 MeV, below this energy, these neutrinos are very good at probing the properties of the sun. For example, now there's some argument in terms of what is the metallicity of the sun. And For example, the CL neutrinos are excellent probes of properties like that. And above that, it's the high energy branch. And there's two. One is boronate neutrinos. And the naming of these neutrinos are very straightforward. Neutrinos come from boronate decay, so boronate neutrinos. And HAP neutrinos, which is helium and proton interaction. So there's two. And boronate, we've measured for 20 years, and this branch has been used to do neutrino oscillation study. And the other one, HAP, which is order of magnitude lower in flux, has never been measured before. So the boronate HAP will be the focus of my talk today. Just so that you get used to these two names. Any questions so far? No? Okay. So next, I'll explain a little bit how boronate neutrinos actually oscillate in the sun. And I think the physics is really simple and interesting. If it's too simple and you all know it, please let me know. I'll skip it. So now we know that we have this standard three-flavor neutrino oscillation paradigm. But in the sun, the oscillation is quite simple in that there's only 2 degrees of freedom involved. So what you can imagine is a system of 2 flavor eigenstate, nu e and nu mu. Correspondingly, there's 2 mass eigenstate, nu1 and nu2. And they don't align, so they're connected by a rotation matrix. And it's the normal cosine theta, sine theta matrix. So there's one angle that controls how these eigenstates rotate. And in the meantime, there's also a delta m squared difference between these 2 mass eigenstates. So 2 parameters governing this oscillation system. And if you just solve a standard first-year quantum mechanics system of 2 levels, this is something that you will get. So in the sun, the neutrino oscillation is expressed in terms of the survival probability, meaning the probability of neutrino produced as nu e, which is 100% of the time, and that are still detected as nu e. And you see a normal sign function. 2 things I want to point out. So this pattern, this height, this amplitude, is controlled by the angle. And the phase of this oscillation is controlled by delta m squared. And go with delta m squared is the quantity called L over E. So the neutrino energy and the neutrino baseline. So this is the pattern. But actually, it's a little bit more complicated than this. Because in order to see this pattern, if you want to measure this, what you want to do is you pick a phase point, measure this amplitude, that gives you angle, and measure this position, that gives you delta m squared. But in order to do that, this quantity has to be on the order of 1, which would give you an oscillation length about 100 kilometers. But solar neutrinos are produced in the sun, in the region much larger than the oscillation length. So solar neutrino 1 and 2 that will reach your detector probably differ in this quantity by many pi's. So this quantity has to be averaged over length. So we all know how to average over a sine squared. That's half. So to take that into account, what you would expect of the oscillation probability of solar neutrinos is just a constant number. And it does not depend on neutrino energy or delta m squared. This will be an important point later. So how does that look in a normal-ish plot? So this is survival probability on the y-axis as a function of solar neutrino energy. This is the canonical plot that people show for solar neutrino oscillation. And I just realized that the gray line did not show up at all. So basically, there's a flat gray line that goes from here to here. It's completely flat, consistent with the error, but the point is the line stops at here. This just to show that if the previous slide were completely right, then what you imagine of solar neutrino oscillation will be incredibly boring. It's flat, you measure that, it gives you an angle, but no information on delta m squared. So luckily, in the sun, it's a little more complicated than that. So what happens is neutrinos interact very weakly with matter. So if you count a solar neutrino going through the sun and have a hard interaction with something, the probability is very small. But because the solar matter density is so high, neutrinos would experience an effective matter potential. So what happens is when neutrino propagate in the sun, the effective Hamiltonian will be modified. So this is the so-called matter effect in the sun. And you can understand as this. So this shows the effective mass of neutrinos M1 and M2 as a function of electron number density. So when the electron number density is very low, this is basically mass 1 and mass 2, and that's the normal vacuum regime. When the electron number density is very high, basically this thing gets modified. So if you want to calculate what's the neutrino oscillation probability going through the sun, the easiest way to understand it is you have to integrate through the Hamiltonian as the path length. And in the end, you will get a survival probability that looks like this. Basically, it depends on the vacuum oscillation angle, and that's the normal angle. But it also depends on where neutrino is born, as that's the initial effective oscillation angle. Okay, so if we want to see how does this look on this figure, this is really unfortunate. So earlier I said it's a flat line that basically goes like this. Now there's a line on top of that. It's very smooth. It's slowly changing. That basically traces this line. It goes here. And so what happens is above, say, 1 MeV, neutrinos start to experience matter potential, and that oscillation probably get modified. So this is slow change, and then it plateaus flat at higher energy. So this introduces matter potential at higher energy, and vacuum oscillation in lower energy. And one thing that's good that you don't have to see the gray band is that gray band basically lie on top of the experimental measurement. So these error bars are various measurements from various solar neutrino experiments. Any questions?
So the invisible green line agrees with all the error bars?
Exactly. So if you, so that's the message you will get. You can see the gray line, the gray band, like goes here and goes through here. So if you look at this figure, you might think, oh, cool, the experiment theory agrees, nothing else. But actually, that's a kind of misleading figure to show. Because there's another place where you can look for the matter effect in the sun. What happens is, this is the so-called, So earlier the gray band that you cannot see, it basically, it's like upturn, it goes like that. And earlier there's a longer flat line at lower energy because that was a long x-axis. So if you put the same curve on the linear line, it looks either like the purple or the orange, given fixed set of oscillation parameters. But then there's another matter effect for solar neutrino. That's the so-called day-night effect. So for solar neutrino to reach us at daytime, it needs to go through the sun and basically nothing else than vacuum. But for that to happen at nighttime, the solar neutrino basically need to go through also the entire Earth. And because the Earth core has very high matter density, that would add a little matter effect on top of what I already described. But that effect is minor. So let's pick this orange band. The day and night difference are the dashed and the solid line. You see it's a little different. It's like a few percent at the highest energy. And at low energy, they start to converge. And one thing I want to point out, just to keep in mind, and this day-night effect, roughly speaking, grows linearly as a function of neutrino energy. Okay, so any questions at this point? No? Okay, so basically two effects we can look for. One is the upturn at lower energy. One is the difference between day and night solar neutrinos reaching us. And unfortunately, there's no figure that I can lay data point on top of this figure. So the result is summarized by this. For CAMLAND reactor neutrinos, the way that the measure neutrino oscillation is the first slide, the sine function, in vacuum. Because the reactors they're close to their source and the oscillation is just like a vacuum. So what they really measure is the oscillation. They measure the height of the function, which gives you an angle, and they measure the position of the peaks, and that gives you delta m squared. So it's really in the oscillation sense. And that gives this value. But for the solar, through day-night measurement, the delta M squared disagree a little with the reactor best fit. And that's the measurement. Now, this is a 2 sigma tension, or 2 sigma hint. So the question is, why do you care about these 2 sigma tension? Well, there's a couple reasons for me. The first is, when you look at this figure, you might think, oh, if it's really the same physics measured by 2 experiments, but they disagree, then you can more easily imagine maybe one experiment did wrong, or maybe it's just a signal fluctuation. But one thing I really want to emphasize looking at this figure is the physics of these 2 measurements are really, really different. The reactor truly measures a oscillation in the sine function sense. But the solar measurement, rather than saying it's an oscillation effect, what you're really measuring is neutrino-matter interaction, weak interaction that's accumulated through neutrino going through the entire sun. So it's plausible that if you believe there's some beyond standard model neutrino interaction with matter, then that would affect this solar measurement, but that would not show up in the reactor measurement. So for example, there's no shortage of BSM models that try to explain this. So let's look at this NSI. So what this means is, on top of the standard weak interaction, there's extra flavor-dependent neutrino interaction with a quark. So that's the effect of Lagrangian written down. So if you have this, then you would modify neutrino interaction in the sun, and that would change your survival probability of this upturn into something like this. And this is not constrained by current data compared to the standard case. So stuff like that would affect solar neutrino, but they will not show up in reactor neutrino. So that's one reason. Another reason to me, as a phenomenologist, is that if there's a 2 sigma tension in the data set, I want to kill it or confirm it one way or another. But unfortunately, for this 2 sigma tension, it's been there for quite a few years, and there's no promise on the market, given the current experiments, that this situation would ever improve, in a 10-year timeline. Why? Because this is incredibly difficult measurement, and there's fundamental limitations in what we can do to measure that. So next, I'll talk about why this measurement is so hard, and why we don't expect this is something that go away in, say, 5 years. Any questions at this point?
So which way does the tension go? You would need a bigger matter effect or a smaller matter effect to make the solar agree?
Good question. You want a small, now we're measuring too much matter effect. Right. And this, right, I'll talk about that later. Basically, it's essentially come from super K that's measuring too much day-night difference than Kaplan expectation. Okay, so just to make this point very, very clear, in the solar neutrino sector, what do we want to measure? First, we want to measure overall level, like y-axis position of these lines. So what they mean is, you want to measure the survival probability of electron neutrino. So you want 2 things. You want to measure the electron neutrino flux, and you want to measure the total neutrino flux, and you take the ratio, that's what you want. That gives you the position of this line. And on top of that, you want to measure matter effect, which gives you delta M squared. So you either want to measure this upturn, which is just direct show up as energy dependence, or you want to measure the day-night difference, which also shows up basically linearly as a function of neutrino energy. So you want to measure nu E fraction as a function of neutrino energy. That's what you want. So how can we measure these neutrinos? Contributing to the current data set, the largest 2 contributors are SNOW experiment and Super K experiments. So first, SNOW. This is, hopefully everyone has heard about it. It did this beautiful solar neutrino measurements that has already finished. And it's won the Physics Nobel Prize for solar neutrino measurements. The thing that's great about SNOW is made such that it had multiple channels to measure solar neutrino spectrum. So first, it has a neutral current channel, meaning that it's equally sensitive to nu e, nu mu, and nu tau. So neutral current channel gives you a measure of the total neutrino flux. Then it also has a charge current measurement. It's only sensitive to nu e, so this can tell you what's the survived part of the neutrino spectrum. And I'll skip this and come back to it later. So another way to show this is this figure. So the x-axis shows the measured nu e flux, and the y-axis shows the measured mu plus tau flux. So when you have a neutral current measurement, you measure the sum of x and y, so you put a measurement like that with an error bar. When you have a charge current measurement, you measure nu e, but you're not sensitive to y, so you have a vertical measurement with this error bar. So just imagine these two bands intersect, boom, you know what's the ratio with the error. So this illustrates the beautiful idea behind snow measurement. So in terms of contributing to current data set, in fact, because snow was small by current standard, right now it only provides the total Born-A neutrino flux. So basically this neutral current measurement. And it measures the total Born-A flux to 4%. And we have to rely on this measurement because theoretical predictions of this flux is worse, and it's something like 14% error. So this is one constraint that we have to rely on today. And on top of snow, the other experiment that contributes to the current Joule square measurement is Super K. So I'll explain this in a little more detail. Super K is a water detector. So it has only one channel to measure neutrino, and that is neutrino electron scattering. So an MEV neutrino comes in, you see this recoil electron. And so because of this, you're basically sensitive to all three flavors, E, mu, and tau. But because this extra charge diagram for nu E, it's more sensitive to nu E. In another way, if we look at the cross-section of neutrino versus neutrino electron scattering, you're measuring an effective flux of nu E plus a sticks of mu and tau, and this is just a cross-section ratio. So this is fine on its own, but it shows one problem in Super K measurement. You only have one channel, so you're only measuring this combination of the flux. You need another channel so that you can take the ratio to get nu E flux. So that's where the problem comes in. Because there's no other channel in Super K, it combines the snow measurement of the neutral current that gives you 4% of Born-A. So in fact, the angle measurement by Super K now is limited by the 4% flux measurement from snow. And the problem is snow finished, so that measurement will never improve. So we're stuck with basically limited systematic errors on the angle measurement. Does that make sense? Okay. So then another more serious problem to me of this channel is this. So because you're only measuring outgoing electron, and you want to infer everything back to neutrino energy, so what you want is a truthful relation between the outgoing electron and neutrino energy. And that's not what we get in this channel. Here I show the differential cross-section as a function of electron recoil energy. Basically, the idea is if there's a 10 MeV neutrino energy, this electron is more or less equally probable to show up anywhere between 0 and 10. So what you see in this recoil spectrum is a kind of reverse integrated feature of everything happened of neutrino above that energy. And remember that when we trying to get delta square measurements, all these features depend on neutrino energy. If you integrate everything, that obviously degrade your sensitivity quite a bit. But this is not something that we can change because it's a water detector. This electron is all we can ever see, and the kinematics is just the way it is. So this is why the day night effect in Super K, it's very nice, it's a few percent, which is not that small of an effect. It has a linear dependence on neutrino energy, which should have been great. But because we can only measure everything in electron, it got kind of washed out. So after 20 years of Super K running, there's less than 3 sigma significance on the day-night effect. That's why the error on delta square in solar is so large. But because of this we don't really expect to get better in any time because it's been running for 20 years. Running extra 10 or 20 you just don't see that error to shrink in any meaningful way. Okay, so that comes to finally our project. Basically, up to this point, solar neutrino measurement is a little bit stuck because we're stuck with 20 years of super case statistics. It's very hard to improve upon that. Now, a new opportunity arises when Dune got approved. So, first, if you're not familiar with Dune, the main science is really, it's a GeV long baseline neutrino oscillation experiment. So what happens is they accelerate a neutrino beam at Fermi-lab and send it to, there's a very large far detector that's really, really far that measures how these neutrinos oscillate. And the neutrino beam have energy about a few GeV. And what you're looking for is oscillations pattern like this. So in an accelerator neutrino, you get mostly nu-mu, and you want to see how much of that those nu-mu turn into nu-e. So this is the so-called appearance channel. And that's sensitive to the value of delta CT and also mass hierarchy. So these two are the main parameters that Dune is going after. But for our purpose, we're interested in how the detector would work at MeV energy scale. So we skip everything about beam neutrinos and we just focus on the large far detector. It's very exciting because it is gigantic. It is 40 kiloton of liquid argon that detect charged particles. And so practically it's actually 4 10 kiloton modules that will go in one by one. So for our purpose, we will not go into how the detector actually works, and we'll only rely on these assumptions. And actually we'll talk about these assumptions later on. The first is we assume that detector can trigger on MEV event. We'll talk about that later. And because Dune is designed to catch the next galactic supernova neutrino burst, it does have MEV capability, and that's listed in the design document. So it's supposed to be able to detect any electron above 5 MeV with high efficiency, with a 7% energy resolution. And on top of that, we assume that it can measure an electron track with angular resolution of 25 degrees. So these are taken from official design document. This is from a previous liquid argon detector study, and that's something we'll talk about later. So these are all you need to know so far. Any questions?
Is that the energy resolution of just the electron?
Correct.
Okay.
So this is for supernova. So this is energy resolution from like 5 to 30 MeV electron.
It's 25 degrees for MEV electrons.
Correct.
Okay.
So because in fact this is from taken from an Icarus study, which is the previous smaller liquid argon experiment, and there was a solar neutrino study in Icarus, and they did like basically simulation of see what you can get. So we take their value because there's no official Dune value. Okay. So why are we so excited about Dune? For MEV purposes. Argon. Argon is the answer. What's nice about argon is that there's a mu-e interaction with argon, charge current channel. Now, this is super exciting. And the reason is, generally speaking, if this is nucleus interaction and this charge current, the cross-section tend to be quite large and then compared to, say, neutrino electron scattering. And so this is the diagram. And typically, this doesn't happen in most materials because, for example, this doesn't quite happen for argon because for normal nucleus, this interaction has quite high threshold. What I mean by threshold is, say a 20 MeV threshold or 50 MeV threshold is quite common. So if you had to guess, that could be your value. But for a 50 MeV threshold, then you can't really do any measurement of solar neutrinos because all the neutrino energy would go to overcoming the threshold. So the thing that's really, really exciting about argon is that this can happen and the threshold is low. So for neutrino to go to ground state of potassium, the threshold is only 1.5 MeV. So there's no penalty in terms of making this happen. Now in reality, the it doesn't go to ground state, so it goes to a few excited states. So the effective threshold is something like 5 MeV, which is still quite low. So that's the super nice thing about this interaction. And in the detector, what happens is there's an outgoing electron, which you can see, and there's also a excited potassium. So this potassium will be excited, gives you gamma. So in supernova neutrino detection, people talk about, tagging this gamma together with this electron, blah, blah, blah. We don't want to assume any super fancy particle identification tagging technique. So for our purpose, we just ignore everything happened here. So our signal is the outgoing electron out of this interaction. So that's really nice. Now, given that there's this channel, why do we expect there's anything interesting of doing solar neutrino in Dune? Because supergas has been running for a long time with very large statistics. So if you see this interaction, there's a couple of reasons you can come up with that would expect there's some nice results of doing solar neutrino in Dune. So this should just give you a conceptual idea. So the first is, in Dune, there's this charge current channel, and because everything has electron, there's also this electron neutrino scattering channel. So these two channels combined would give you a basically flat crossing. So it's the same idea of the Snow figure, mu E flux on x-axis, mu and tau flux on the y-axis. Now, if you can measure a pure charge current flux, it gives you a vertical band, and this red band with this thickness is what Dune can do statistically, compared to the Snow old charge current band, which is this big. So you see, Dune charge current statistics is amazing compared to what Snow has. And then Snow has neutral current that's its width that Dune does not have. But because Dune has this electron scattering channel, it can also measure the flux in this way, and that's the screen band. Because it's mostly sensitive to mu E, so it's kind of vertical, but it's tilted slightly. And Dune two channels combined give you this crossing of this bright green region, just to show that it is much smaller than this shade from Snow. And this is a statistical only statement, just to show that because Dune is so huge, with the new charge current channel, we can, in principle, believe that Dune would improve on the angle measurements of Snow. Any questions about this? Okay. So another exciting thing is on the delta square. So as said, to measure delta square, you always want to measure things as a function of neutrino energy. And the nice thing about charge current channel, it's just a golden channel. The nice thing about charge current channel is, because this is basically a two-body final state, you have very tight relation between the electron energy and neutrino energy. So it's just subtract Q value, which is the threshold of 1.5 MeV, go to ground state, and whatever the excited state. Because it goes to a few excited states of potassium, this is not exactly like a one-to-one relation, but it is still a very tight relation compared to, in the electron channel, everything is completely smeared. So this tells you that if you measure this channel, what happened in electron, it quite faithfully tells you what's happening in neutrino. So based on this, we expect that Dune can improve on delta squared. Okay. Now, how we actually do this analysis? So one critical assumption is that you have to be able to separate these two channels, charge current versus electron scattering. Luckily, this happened quite naturally. For charge current, because it's a nucleus interaction, it's the outgoing electron is isotropic. For electron scattering, the electron is peaked forward. So again, we don't want to do something too fancy, so we just assume a very simple cut. So you cut forward cone of 40 degrees, and that's the only separation. So inside this forward cone, you would expect the mostly electron scattering event, and outside this forward cone, this isotropic region, you would expect mostly charge current. So this is what we show. And with exposure of 100 kton-year. This is all the event rate we have. So let's look at the lines. So in the isotropic region, the largest thing is born a charge current. And one thing just to see, there's a lot of events. So this is 10 to the 4, 10 to the 5, which is enormous for neutrino experiments. And then out in the region, there's some leftover electron scattering background, and that's this line, but not too much. And there's also this background line, which I'll talk about later. One nice thing is look at this HEP CC. So I haven't talked about HEP except for on like slide 1. Basically, it's never been detected because the flux is so low compared to boronate. But nice thing about HEP is it's a little bit higher energy than boronate. And in previous experiments, mostly neutrino electron scattering experiment, the HEP curve never showed up because the effective smearing in our experiments would be very bad. So imagine this boronate curve that got a much worse energy resolution. It's going to completely cover up the HEP. So it never showed up before. But now, because this great kinematics in the charge current channel, the HEP flux peaked up a little. So you can roughly eyeball it saying, above like 12 MeV, there's about 100 events. So you can roughly expect a detection of, 10% error. And that's in fact very close to what we get in the end. So this is the extra detection. And inside the forward cone, you mostly get electron scattering and with a little bit of contamination from all other channels. So based on this event rate, we fit for the parameters, and this is what we get. So right figure is this color contour is what Dune can do with 100 kton-year exposure. Compared to, this is the same scale, compared to the color contours from the current combined solar. You see it's drastic improvement, certainly on Dalton square, and it's might not be so visible, but there's also improvement on the angle. And also at this contour. So this 3 black contour is the current generation reactor experiment from Hamlet. And China is building a proposed next generation reactor experiment, Juno. And it's just incredibly precise. This is its 3 sigma prediction of how well it can measure these 2 parameters. So if this tension or hint is real, it's actually caused by some new BSM physics, then Dune and Juno combined can attest this tension to almost 5 sigma. And in addition to this, we can also improve the boronate flux measurement from 2% to 2.5%. I think it's really cute because the current angle measurement is really limited by the 4% measurement. That's from the experiment that's no longer run, which is nice. And we can actually make the first detection of HEP flux with 10% error. So, any questions about this? Okay.
Is the nuclear physics well enough understood? So to reconstruct the energies of the neutrinos, you need to be able to understand these excited states, these nuclear transitions in excited states, and so on. So is that's under control?
Great question. Two-part to answer that. First is, so what we assume is that you only detect this electron and you don't reconstruct the neutrino energy. So our analysis is actually done just using electrokinetic energy, because we don't want to reconstruct neutrino energy, you have to collect these gammas as well. We just don't want to make any assumptions, so we don't actually rely on that.
But you must be using that because you're measuring an oscillation effect, so you're looking at the dependence on the electron energy on the electron, so you use the model for the nuclear physics, right?
Correct.
So
Yes.
it's still the same question, right? You have to know that that's reliable.
Correct, and that's the last slide. It has some effect, but it's not going to kill the Dalton square.
So you're saying the theoretical uncertainties are under control, that's not an issue?
Yes.
The modeling, whatever you want to call it, the modeling uncertainties of the nuclear.
Yes. Any other questions?
So the neutrino electron scattering is on top of the charge current channel.
Correct.
What's the event ratio between the 2 channels in you? How do you separate the?
That's a great question. So I should actually know what's the event rate in these 2, but I don't remember the number. I can get back to you on that. But here the separation is what we assume. So we assume the angular resolution is 25 degrees, so you're able to do a 40 degrees cut, angle cut. So you see in the inside forward cone, it's mostly electron scattering, but obviously the charge current contamination is non-negligible. And I guess in the isotropic part, electron scattering probably is less of a concern in terms of background for charge current. Right, so that's the separation we assume.
Okay. But inside the 40 degree cut, you still have a, you
Charge
cannot,
current.
yes, you cannot remove the charge currents.
Right, and that's taken into account in terms of background. Okay, so up to this point, I think it shows the physics case of what Dune can possibly accomplish measuring solar neutrinos is very exciting. But I certainly don't want to mislead you into thinking that it's going to be a very easy, straightforward measurement. So there's a few aspects that are potentially problems that needs to be thought about carefully and worked on. And here I'll talk about a few. So the first is trigger. So the idea is Dune is mostly designed to be a GeV machine, so at higher energy. And so then how well it can trigger if you want to trigger at lower energy, typically data rate is a concern. So this kind of shows the idea. So this is the event display from Microboom, which is a currently running liquid argon experiment. So it's the same technology as Dune. So here a neutrino event a beam neutrino event, a GeV event, or hundreds of maybe look like this. You see it's a tracking detector, you see this clear track and long track clear. But how does an MEV event show up in such a figure? It will probably look something like these. There's a dot here, if you can see, and there's two dots here. So basically, the event will look something like that. When a beam neutrino interact, it's going to make a beautiful large splash event. But then if you want to look for MEV stuff, it's like very short blips of events. And in the detector, any second there are a ton of those little things happening. So the data rate at MEV will be quite high. Super excited. So I thought this will be a main problem. But super excitedly, I think recently Dune has decided that they can essentially self-trigger on any event that is larger than 10 MeV and collect all the data. So 10 MeV is a lot closer to 5 MeV than not be able to self-trigger at all. So to me, that's a great news. But still, they need to be able to actually self-trigger anything above 5 MeV for this to work. So that's one concern. The next problem is background. So in my main figure, I only showed one background line, which is the sum of all three. So I'll explain what these are. So let's start from the least important one. So the higher energy, there's this oscillation. What this is high energy cosmic ray muons can enter your detector, and they'll interact with argon, break it up, produce something beta unstable. And that one will beta decay, that gives you electron. Because our signal is an electron coming from the charge current or electron scattering event, anything that produces MEV electron will be a background. So that's the spatial one. Luckily, Dune is very deep underground, so the muon rate is not very high. So given standard oscillation background rejection technique, this is what we can get after the cut. So overall, we're not too concerned about this background. The next one is neutral current interaction. So neutrino can also interact with argon through neutral current interaction, give you excited argon. The argon will gamma decay and give you gamma, which will show up as electrokinetic energy. And this cross-section is quite uncertain, but given our standard reference, this rate is quite low. So we think that it's not too much of a problem, because if it's really this low, you treat it as a background, it's not a big concern. If it's much higher, then you can in turn turn it into a signal. So overall, we're not too concerned about the neutral current background either. The problem is unfortunately this neutron capture. What this is really unfortunate. So Dune is underground in the mine, and it's surrounded by rock. in rock, there's uranium and thorium, just normal radioactivity that's present. And these guys would alpha decay, and the alpha would then interact in a nearby nucleus in rock, say silicon. So this alpha would interact with silicon and produce a neutron. I know it's quite confusing. And this neutron would have very low energy, a couple MeV, and that would enter your detector. So in a typical underground experiment, there are always these neutrons, trying to come into your detector. So if outside the detector there's shielding that would try to stop these neutrons, then you're fine. But Dune is not designed to do that, so Dune has no shielding. So these neutrons can just come into your detector, reach liquid argon. And once they reach liquid argon, they can travel, across the whole detector and then capture, which would give you a 5-ish MeV gamma ray. And that gamma ray would show up as the electron, and that's this background. So from the way I described, you can see that it's not something, it's not very easy to cut, and because the site has already been selected, so the contamination level in the rock is already fixed. So there are a couple ways, there's a few ways to beat down this background, and I'll just clearly state our assumption. The background, without doing anything, for this line, is about 10 to the 3 times higher than this line. That obviously doesn't work, so what we assume is, let's first just assume there's standard shielding outside Dune. And standard shielding is basically something that's either filled with water or plastic, You just need hydrogen. And to beat down that background level from 10 to 3 times higher to this level, we need about 40 centimeters of shielding. So we take this as our standard assumption. But you might think 40 centimeters of shielding outside Dune might be impossible, and then I'll show later how to fight for that, if there won't be 40 centimeters of shielding or less of that. So I think this is still the best figure to show this. Keep in mind, so if this line position is higher, what would happen is the signal line is kind of flat or smooth here. So what you're effectively changing is the effective threshold of the signal. So given this background level, the effective threshold for analysis is actually about 6 MeV. So then what we tested is, what if you just raise the threshold and see what would that get you? If we raise the threshold to 6 MeV, this is what it will look like. So there's black dotted line inside. That's quite similar to the color contour. So the black dotted line is our standard assumption. But you can kind of see the trend. If you raise the effective threshold, the contours will get fatter on the angle side, roughly linearly, or square root of linearly. But then it will get taller a little faster than that. So you take a bigger hit on the delta square and smaller hit on the angle. And it turns out that this loss in sensitivity from raising threshold solely comes from the fact that when you raise your threshold, you just lose statistics. You just have theory events. So then we say, okay, if we try to reach our nominal assumption, but compensate for the statistic, obviously can be done through exposure. So what exposure would you need for a certain threshold if you want to reach our nominal level? So the black dots are the value. So our standard exposure is 100 kton-year, so that is 2.5 human years of actual running time. That's if you can reach 5 MeV threshold. If you go to 6 MeV, you basically don't lose much because of the background. It's very close to the effective threshold. If you can only go to 7 MeV threshold, exposure doubles, which is still not too bad because 5 years is quite reasonable. And 8 start to become to the edge. 10 years running is the standard assumption for one generation neutrino experiment. If you go to 9 MeV, then the exposure you requires start to become unreasonable. So basically, this is what we think. If you can add shielding with good energy resolution, then you need lower threshold. If you can't make that much shielding, or the energy resolution gets a little worse, then it can be somewhat compensated by going to a higher threshold. but you have to go to at least below 8 MeV for the result to be reasonable. And one thing that's not shown here is, another thing that's possible is, in our current signal versus background, we only consider electron, which is conservative. If they're able to tag external gamma from the charge current interaction, that will beat down the background. But we don't want to assume something like that, so any efficiency they get from there would help, but we don't quantify that.
I thought the neutron also has a gamma, the neutron interactions?
Yes.
So you would have to be able to use some details of the kinematics of the neutron.
Exactly. Yes. So if they can separate a 5 MeV electron track versus basically a 2 plus 3 MeV gamma make up something, then that will help. But it's too hard to say how well they can do.
We might have a chance of doing it. So I work on energy neutrino physics and Dune, and Bob Svoboda and some of the rest of our group here, we're actually measuring the gamma cascades from neutron capture and argon. We don't have data for it. There's a few gammas that are known, but we're actually measuring the pattern. Hoping to get measurement of that in the cross-section out here published pretty soon. But I think it's not crazy to think that we could actually see the de-excitation gammas in Dune. So in the APS April meeting, the Argonaut folks presented some slides where they showed clear evidence that they were seeing de-excitation gammas where we could resolve those. And so we have a fighting chance. We may actually be able to do better on that part.
Yeah, that would be super, super helpful for this. Yeah, and the last point is, as you already asked, cross-section. So for our nominal assumption, we assumed no uncertainty on cross-section, just to keep it simple. And it's a little hard to say what exactly is a current cross-section uncertainty in this energy range. Because theoretical and experimental measurement, they quote some uncertainties, but then sometimes two results differ more than that. So the smallest uncertainty quote from work is as low as 2.4%. But we want to say it's probably a few percent. Should be definitely less than 10%. And if we think the cross-section uncertainty is 1%, the color region is what we get compared to the black dotted line. So what you see is it gets fatter. And the reason it's on the angle, the sensitivity really comes from charge current crossing electron scattering. So if you move the charge current normalization, then that will make the angle worse. But because the delta M sensitivity really comes from day-night asymmetry, that's just in charge current, so that essentially cancels. So you don't really degrade in the vertical range.
So the dotted line should be compared with the green color.
So, okay, so the red, green, purple is new 1%, 1, 2, 3
Yeah.
sigma. That should be compared to the black dotted. That's our nominal. Sorry, it doesn't.
Yeah.
So basically, the vertical, if you can take my word for it, the vertical didn't get any worse, but the horizontal got fatter. So that's 1%, and yes.
I just had a question. All these projections seem to depend on the fact that what you're doing is you're taking the original measurement and you're just lowering the error on it. But that assumes that the original measurement is actually correct where it's centered there. What you may find is you make a new measurement, it's actually much closer to that little dot up there. I mean, is there any reason to believe that that's where you should be looking?
No, that's a great point, and I thought I put that in my backup slide, but I don't. But I can show you. We also, right. So because one of our main motivation to do this is to emphasize the stiffness, that's what we chose to show our nominal results.
Yeah.
But we also have results showing how the sensitivity will show up at higher value. But what you can see is no matter, and the contour get a little worse than this size, but because Juno will be able to accomplish this, if the true value is really indeed here, then of course it's not even comparable to what Juno can do. So really the benefit comes from if it's indeed different, then we can test this difference. But that's the 3 sigma sensitivity. That's just so incredible that it's not obviously not comparable. That's
The first thing you may find is that in fact the orange dot moves upward or something. But the effect
Yes.
tends to go away. It was
Exactly.
actually maybe statistical. So
Yeah.
anyway, that would be
Exactly.
used as well.
Well, if we can confirm that there indeed the there's no tension in the sector, then that's also great. This is just to show roughly how well we can do. Right, so if the uncertainty we assume is 10%, which I think is worse than the current situation, then you really lose a lot of sensitivity horizontally. So you have to use the current, rely on current measurement, and then you can improve on the angle by a little bit. But 10% certainly you lose most sensitivity on the angle. But still, it doesn't really degrade on the y-axis.
What are these contours that are big in the y-axis, or is that just something else from the plot?
Oh, sorry, that's the current solar contour.
Oh, okay.
That's
All right, yes, I see.
right,
Sorry.
because for this we have to rely on also using current data. This is all assuming Dune alone. Yes. Okay, that brings me to my conclusion. I think it's really, really exciting that Dune has the possibility of doing solar measurements because given the current solar situation, I think it will be great if we can have another experiment that can measure solar that could potentially have such incredible sensitivity. And Dune is a really large liquid argon experiment, which is expensive, and we'll probably never get one that's this amazing again. And we think doing solar in Dune can obviously benefit solar neutrino physics, but it also enrich the physics program of Dune. So hopefully they can accept our proposal and do this measurement. Thank you.
Do you have any more questions?
So I wanted to follow up on with Marcus's question. So you were showing that plot where you were saying, here's our expected distribution for the final electron kinetic energies. You talked about the uncertainty on the cross-section, which I take to be probably the total cross-section. But for predicting that distribution, what you really want is the partial cross-sections to each nuclear level, because that determines the Q value. Can you tell me how that calculation was done? Because that has to be done very carefully.
Oh, so good question. So that calculation has not been done enough. We can show the results. So this is just show the total cross-section error. It's just one normalization error. And in terms of the distribution, we have some preliminary calculation to show that it doesn't degrade the sensitivity much. Because again, basically in day-night, it changes the strength, it changes the energy by like bumpy-like structure as opposed to smooth spectrum. So it's not very sensitive, but we do not have results that show how we vary strength individually and how that will show up. That's something we want to do in the follow-up paper.
Okay, yeah, so the individual strikes the uncertainties on, but what were you using to get the original distributions? You have some nominal distribution, right?
Oh, so what cross-section did we use?
Yes, what cross-section are you using to say to this nuclear level we have this branching, this one we have this branching?
Okay, so we take we took a experimental measurement from Washington, and they measured PN scattering on argon, and so they have basically measured the gamma teller strength. So we use this measurement. So I think the same group did two measurements. One is titanium beta decay, one is PN, and we chose to use PN over titanium, and we chose experimental measurement over theoretical calculation.
Okay. Yeah, I'm aware of those two. Those definitely are reasonable. They kind of agree. There's some tension.
Right. There's one state where the difference is a little larger. That's why we chose the PN data as opposed to the titanium.
Yeah, you can argue which one's better. I'm curious, how high in energy did you go? Did you not need to go beyond the tabulated energies? Because there's expected to be gamma teller strength above where they were able to measure.
Right. No, we don't. We only go up to the excited states of, that's the last one, so 8 MeV.
Okay.
But I didn't think it measured too much for us because we impose, there's 5 MeV, because the solar energy is much lower than supernova neutrino.
Yeah.
Right?
You can probably get away with it just as long as you are careful with it.
So for us, it's actually a lot better than supernova neutrino. Yeah.
Any more questions?
What's the time scale of Juno?
Neutrino, I think it's similar to Dune. It's under construction. I believe the data taking is on the order of 2020. I think these are all 10-year 10-year scale.
Yeah, as far as construction, so there are prototypes over at CERN called the proto-Dune. So there's a single-phase liquid argon TPC and a dual-phase liquid argon TPC. They're prototypes, and they're smaller in scale, so those are under construction. They're starting to dig the caverns for the full, 40 kiloton liquid argon phase detectors, but work on building the actual final big modules for the far detector hasn't started yet. They're doing this prototype experiment at CERN first.
Yeah, that's supposed to take data later this year, so that's very exciting.
Yeah, it's coming up pretty soon.
Yeah.
Earlier in the day-night plot, you showed the difference. Why is there a day-night difference for Camden? I thought it's not
Oh.
solar. It's a measuring the reactor neutrino.
That's an excellent point, and I should have made that clear. So this is, right, sorry. So this is solar neutrino oscillation. If we use Kaplan best fit value for the delta square and sine, the angle, and if we use super K best fit value, so this is show that what's the theory prediction on solar using these 2 points. But this is, right, this is for solar calculation. That's a great question.
Oh.
Sorry, that wasn't clear. I see. Right, so for Kaplan, there's no thing. It's Kaplan best fit values.
I think this depends on how well you can measure the low energy electron track and reconstruct the electron energy from the organic direction.
Yeah.
Do you know how well the liquid argon TPC can track the electron in this energy range?
Right, so which is, so threshold and energy resolution, these are just the numbers we quote of CDR. These are my words. And I think if you ask different people, they'll have different answers to how well they expect they can Dune can accomplish this. We don't want to get into that. So these are just our standard assumptions.
Yes, thank you. Another question is, so Stephen, he has done some simulation for supernova neutrino, and the result is 30% of the supernova neutrino has neutron emission. So how about
Yeah, for solar it's going to be much lower just because of the threshold. So Shirley is correct in saying that mostly those tabulated experimental strengths to the different levels when you evaluate the nuclear matrix elements, those are mostly adequate. It depends exactly how high in energy in the solar spectrum you want to go. The flux goes down once you get towards the tail, but the cross section goes up. So at some point, you just say, okay, good enough, we'll cut it off. If you go too high, though, you start getting the regime where then you populate the neutron-emitting states. But as long as you don't go too high up in neutrino energy, then you're safe. And so, you got to be careful. But assuming that you're careful about it, then that procedure actually looks like it would be fine. For supernova neutrinos, you get up into the higher tens of MeV, and then you start populating those states quite a bit. That's the reason for the discrepancy.
Yeah, well, that could be solved.
Exactly. So one thing that we're lucky in a sense, the spectrum basically do not go up than 20 MeV, which is things still stay relatively simple. Once you go to 30, 40 MeV for supernova, it's much worse, like in terms of understanding cross section and stuff. So for us, it's not a big problem.
So you mentioned the trigger now is 10 MeV.
Sorry.
The trigger for the.
Trigger is trigger on electron, and we assume that you can trigger on anything that's above 5 MeV.
Okay, but the real technique they can achieve now is that what they can already achieve, or?
Well, because it's under construction, so it's hard to say what they can achieve. But the group that work on simulating this now claim that they can self-trigger on 10 MeV. So meaning everything above.
Yeah.
So there's 5 more MeV to go.
I know, yeah, but I mean, how promising is that? Or if you just assume 10 MeV, does that affect your
Okay, so for us, you definitely need to go below 10 MeV, because this can show if your threshold is 10 MeV,
right.
then to reach good sensitivity of delta squared, you're losing too much events, basically.
Right.
So you have to go
So you
below
really
10.
need that, right?
Yeah. So the extra 5 is, or at least extra 3 is important.
let's thank Shirley again.